The next few lessons will cover information regarding circles. So we've kind of taken the material from chapter 12 and whittled it down to what we think are the most important ideas. So first of all, some definitions. A segment whose endpoints lie on a circle. The endpoints lie on the circle. It's called a chord. Okay, a line in the plane of a circle that intersects it in exactly one point is a tangent. And the point at which the line intersects the circle is called the point of tangency. I'm going to draw a picture of these things in a minute here. A line that intersects the circle in exactly 2 points is called a secant, or a secant line. Sometimes we'll cut off secants and call them secant segments. But when you're thinking about the picture here, so we have a circle. This segment is called a chord. It's going between 2 points that lie on the circle. A tangent line is going to hit the circle in exactly 1 point. It's kind of hard to draw that, but theoretically, there's 1 point right there. And this is a tangent. Sorry about that. This is a tangent. And that point right there is called a point of tangency. That point right there. Okay, and then a secant is a line that intersects the circle in 2 different points. So a secant would be a line like that. So first of all, it's a line, and secondly, it hits in 2 points instead of just in 1 point. So a chord is a segment. Okay, so a chord's a segment that has 2 points on the circle. A secant is a line that has 2 points on the circle. And then a tangent is a line that has exactly 1 point on the circle. Okay, so in this example, tell whether the line is or segment is a chord, a secant, a tangent, a diameter, or a radius. So segment HC. Segment HC is passing through a point on the circle and also the center of the circle. That means the segment HC is a radius. Okay, it's not a chord because it does not have 2 points on the circle. It has one end point on the circle, but the other point is the center of the circle. So that is a radius. All right, segment BE. Segment BE is this segment down here. So for segment BE, since it's connecting 2 points that are on the circle, and it is a segment, that means that it's a chord. Now, is it anything else? Well, it can't be a secant because it's not a line. It cannot be a tangent because it's not a line. Is it a diameter? Well, a diameter has to go through the center of the circle, which is C. So that chord is definitely not a diameter. Okay, segment BH. Segment BH. 2 points on the circle connected to each other through the center of the circle. So that's a chord, but it's also a diameter. So it's a chord and it's a diameter. Okay, line DG. Line DG is that line right there. Okay, so first of all, line DG intersects the circle at exactly 1 point. So that makes it a tangent. Secant lines have to hit in 2 places, so have to hit the circle in 2 different points. So if I had a line like this and I moved it, so it looked like that, that would now be a secant. Okay, but as it's drawn, this line right here is a tangent line. Okay, and then line AF. Line AF is this segment, but it's stretched out to be a line. Okay, so it says line AF. That means you want to think of this like this line instead of this segment the way that it's drawn on the picture. So because it's a line that's hitting the circle in two different places and it's in the same plane as the circle, that means that it is a secant line. In the definitions up here, let me highlight these: chord, tangent, point of tangency, secant. Um, the reason that it says for tangent, a line in the plane of a circle, a line in the plane of a circle, that just means that it can't be like a circle and then a line going through that one point that's coming out at you out of the plane. So it couldn't look like you took your pencil and poked it straight down through the paper and made it stick out away from the plane of the paper. Okay, so a tangent has to be in the same plane as the circle itself. Okay, always, sometimes, or never. A diameter is always, sometimes, or never a chord. Okay, so here's a circle. All right, so a diameter. If it's a diameter, it goes through the center of the circle and it hits 2 points that are on the circle. So a diameter has to be a chord because it is a line that, a segment that is connecting 2 points that are on the circle. So that is always. Okay, how about a radius? All right, well, radius, always, sometimes, never a chord. So a radius goes from the center to a point on the circle. Well, that cannot be a chord because the definition of a chord requires that it has two endpoints on the circle and then all the points between them. So that is never true. Radius is never a chord. Okay, a chord is always, sometimes, or never a diameter. Well, a chord has to connect 2 points that are on the circle. So that's a chord. That's a chord that's not a diameter. Is it possible for a chord to be a diameter? Well, yeah. A chord that's going through the center of the circle would be a diameter. So that's a sometimes, because it is possible for a chord to be a diameter, but a chord does not have to be a diameter. Okay, and then a tangent is always, sometimes, never a secant. A tangent can only hit the circle in exactly 1 point, so there's no way for that to also be a secant because a secant has to hit the circle in 2 points, exactly 2 points. So that's a never also. Okay, first theorem here. If a line is tangent, if a line is tangent to a circle, then it is perpendicular to the circle, to the radius drawn to the point of tangency. So if a line is tangent to a circle, that means that if line L is tangent to circle Q at point P. So if we know that that's the point of tangency and we're given that that's a tangent, then that tells us that that's going to be a right angle. And the converse of that is also true. Okay, so if L is tangent to circle Q at P, then segment PQ or QP is perpendicular to line L. And the converse of that would go the other direction, right? So if you know that this is a right angle here, where the line and the circle are meeting, then that means that that line is a tangent line. In a plane, again, in 2 dimensions, that's what that means. If a line is perpendicular to a radius at its endpoint on the circle, then the line is tangent to the circle. So if that's a right angle, then you can conclude that that's a tangent. So if L is perpendicular to segment QP at point P, then line L is tangent to circle Q. All right, in this first problem, it says that segment ED is tangent to circle O. So what they're telling us is that segment ED makes a right angle. They're saying that indirectly, so you have to know that that's the point of telling you that it's tangent. So they're saying you can use the fact that that's a right angle. So this problem, all it really means is, okay, we have a right triangle. You can ignore the circle. The only point of the circle was to tell us that that's a right angle because it's tangent. And so that means that 90 and 38 and x adds to 180. Or you can just do x would be 90 minus 38 because there's 90 and that's the rest of the angles up to 90. So that would make it, what's that, 52. Okay, what's the radius of circle O? All right, so for this one, we're using the fact that because that's a right angle, that means that that's a tangent, and we don't even need that. Okay, for this problem, we're told that segment ED is tangent to the circle. So they're indirectly telling us that that segment makes a right angle in the triangle. So this is a right angle. That's the only reason the circle is there, and that's why they told you it's tangent. So all we're really doing is we're looking at this triangle and saying, oh, okay, that's a right triangle. That means that all the angles add to 180. So you could do x plus 38 plus 90 equals 180. My preference would probably be to just go ahead and say that because that's 180 in a triangle and that's 90 degrees, then we just know that x and 38 have to add up to 90, and therefore x would be 52 degrees. Okay, next problem. What is the radius of circle O? So notice that we would know that this segment is tangent to the circle because the fact that that's a right angle. But all we really need to do is look at the right triangle, and we can kind of ignore the circle actually. So because that's a right triangle, we can use the Pythagorean theorem. So we can say that x squared plus 10 squared equals, and that whole hypotenuse is x plus 6, not 6x, x plus 6. So that's equal to the hypotenuse squared. So x squared plus 100 equals, now you have to be really careful here. Watch out for that because it's super important to remember you have to FOIL. That is not x squared plus 36. Okay, this is going to be x plus 6 times x plus 6. X plus 6 times x plus 6. Then we're going to FOIL. Okay, so that'll be x squared plus 12x plus 36. Do x times x is x squared. X times 6 is 6x. 6 times x is 6x. And 6 times 6 is 36. So we have x squared plus 100 is equal to x squared plus 12x plus 36. Now notice that we can actually subtract off the x squared on this problem. It's not even quadratic. It looks like it's going to be, but it's actually not. So 100 minus 36, 64 is equal to 12x. X is equal to 64 over 12. Which is 5 1/3. Yeah, because it's 5 and 4/12, so 5 1/3. Or you could leave it as 16/3. If you took a 4 out of the top and the bottom, you'd have 16/3. Okay, and that would be the radius. Again, super, super important you remember to FOIL over here. It's not x squared plus 36. Okay, next problem. Is segment ML tangent to the circle at L? Well, what that's basically asking you is angle L a right angle? Or is NL, segment NL, perpendicular to segment LM? Those are the same things, right? Okay, so let's see. 7 squared plus 24 squared. We want to know, is that equal to 25 squared? Well, that's 49. 24 squared is 576. 25 squared is 625. Are those equal? Yeah, 625. Okay, so because they're equal, that means yes, because that's a right triangle. Yes, ML, segment ML is tangent to circle N. Okay, and then for this problem, it says segment ML and segment MN are tangent to circle O. What is the value of X? Okay, so we're told that the central angle measure is 117, and we're trying to figure out what is the angle measure at M. Okay, so why did they tell you that those are tangent? Well, that means that angle L is a right angle, so segment OL is perpendicular to segment LM, and segment ON is perpendicular to segment NM. So that means that these are right angles here. So that's a right angle and that's a right angle. So if you look at that quadrilateral here, right, this is a quadrilateral. What do the angles in a quadrilateral add to? Remember back when we talked about quadrilaterals, the angles in a quadrilateral add to 360. Okay, two of those are 90 degrees. That means that the 117 and the x have to add to 180. So you could do x plus 90 plus 117 plus 90 equals 360 and work it out that way using the quadrilateral. I think it's easier to just say, okay, these two angles have to be supplementary. So 117 and x has to add to 180 because we've taken away 90 and 90, we've taken away 180 degrees from the quadrilateral. So that makes x equal to 63. Okay, so I'm going to kind of make this its own little idea here. Anytime that you have a circle and you have two tangents to the circle that are creating a quadrilateral like that from the center. Try it again. Okay, because these are right angles. The angles that are the central angle and the angle on the outside there are always supplementary. Okay, so that angle and that angle are always supplementary. Now that also means, let me copy this again. That also means that if you, let's try it again. Because the central angle is the same as the angle as the arc measure here, so that central angle measure and this arc measure are the same. So like if this was 117, that means that arc measure is also 117. That means that the arc and that angle are also supplementary. So the arc and that angle are supplementary as well. Now, that's only if they're two tangents. They have to be tangents for that to be true. So it has to be hitting at points like that and creating from the center to a point on the outside. Okay, the arc and that angle are on the outside only if those are both tangents. Okay, next theorem. If two segments from the same exterior point are tangent to a circle, then those segments are congruent. That's easy enough to understand, right? That just means that if you have a point out here and you draw a tangent segment to the circle here, and you draw a tangent segment to the circle there, those segments are going to be congruent to each other. So if segment SR and segment ST are tangent to the circle, then segment SR is congruent to segment ST. Okay, so we're going to kind of see that in a few different ways. One of the ways that you'll see that theorem applied is in a picture like this. So in this diagram, it says circle O is inscribed in the triangle. That means that these are points of tangency. If it's inscribed, that means it's just touching the triangle. The circle is just touching the triangle once on each side. Okay, the perimeter of the triangle is 88. What's the length of segment QY? So this is the length we're trying to find. Okay, so we know that the segment here and the segment here are the same. Okay, so that means that one's also 15. And then we have the segment ZR and YR are going to be congruent. And then segment XY is going to be congruent, sorry, not XY, XQ and YQ are going to be the same. So these are both question marks. We don't know what those are. Okay. What we do know is that we have 30 here and we have 34 there. And then we have two question marks. I'm going to call those, I don't know, A, just because I don't want to use X since there's already an X point in the problem. So two of those plus 30 and 34 has that up to 88. So basically we're just saying take away the two 15s, take away the two 17s, and then divide your last value by 2. So 64 plus 2A is equal to 88. 2A is equal to 24. A is equal to 12. It asks you for the length of segment QY. Okay, and that is A is the length of segment QY. So QY is 12. Okay, next problem. So this time we have a quadrilateral, but it's still the same exact idea. So when they say a circle is inscribed, they're telling you that those are tangents. Okay, inscribed is telling you that the segments are tangents. And then circumscribed around the circle means that the segments are tangents also. Okay, so the circumscribed there means that those are tangents. So we have points of tangency that are going to create congruent segments. So we've got these two segments are the same, and we've got these two segments are the same. Okay, and we've got these two segments are the same, and we've got these two segments are the same. Okay, so let's kind of just work our way around here. So if that's 3, that's also 3. If that's 3, that's also 3. If this is X, so is that one. And if this is X, so is that one. Okay, the perimeter is 18 was given in the problem. So we have 1, 2, 3, 4 threes, which is 12. And then we have 1, 2, 3, 4 X's is equal to 18. That means that 4x has to be 6. X has to be 6/4, which is 3 halves, or 1.5. And that's just in units. It doesn't have any particular label on it, so just units. Okay, the next problem says segment AB is tangent to circle C at B. Okay, line AB is tangent to circle C at point B. And then line AD is tangent to circle C at point D. Find the value of x. Well, the theorem said that if those are both tangents from the same exterior point, then they create congruent tangent segments. Okay, a tangent line is what we call a line like that that only hits the circle in one point. If we cut it off, we can call that a tangent segment. Okay, that means that x squared plus 24 is equal to 49. So x squared is equal to 25. We would square root both sides. So technically, when you do the square root of both sides, you'll do plus or minus 25. So that means x equals plus or minus 5. Now we want to see whether we're going to keep both of them. But notice that in this problem, 5 squared will check, but so will negative 5 squared. When you plug in negative 5 and square that and add it to 24, that's equal to 49. Okay, so on this problem, we're going to keep both answers because having a negative value for the variable did not create a negative segment or angle measure. Okay, a lot of times we throw out that negative value, but for this particular problem, we're going to keep both of them. This one should have two answers. Okay, this is the end of the first part of the circles material.